We've spent a lot of time recently looking at variables. These are numbers whose value we don't actually know yet, so we represent them with symbols such as letters. Now, while there's a lot of math that we can do just with variables, they become much more useful if we actually know what the numbers are equal to. Well, the idea of taking a scenario involving variables and figuring out what those variables equal is called solving an equation, and that's what we're going to be focusing on today. An equation is a mathematical statement which says that two expressions are equal. If the equation contains a variable, the value of that variable which makes the equation true, which is the same as making the two sides of the equation equal, is called a solution. Suppose we have this equation, where on the left-hand side we have the expression 3x plus 6, all divided by 5, and on the right-hand side we have the value negative 3, and in between we have the equal symbol, showing that these two expressions are equal. Now the question suggests that x equals negative 7 is a solution. We can check this by substituting the value negative 7 for x into our equation. So if we do this on the left-hand side, we find that we get the value negative 3. Now the equation says that this equals negative 3, so this does make the equation true. So x equals negative 7 is a solution. We can also try substituting a different value, such as x equals 8. If we do this, we find that the left-hand side of the equation is equal to 6 instead of negative 3. This does not make the equation true, so x equals 8 is not a solution to the equation. Now, we're not normally told ahead of time what the solution to an equation is. Solving an equation means to find a solution for it, and that's what most of this lesson and this unit are going to focus on. Solving method 1, backtracking. The backtracking method identifies the operations applied to the variable, then uses inverse operations to work back to the solution. Suppose we have the equation x plus 11 equals 7. Well, we're going to take our variable x as our starting point. On the left-hand side of the equation, this has had 11 added to it, which gives us the expression x plus 11. Now the equation tells us that this is equal to 7. By backtracking, we can do the opposite of adding 11, which is subtracting 11. This gives us the value negative 4. So the solution to our equation is x equals negative 4. Now the backtracking diagram is a useful tool for finding the solution to these type of equations, but we should also get in the habit of being able to write our equations using a more conventional form. The rules here are somewhat similar to when we were working with evaluating expressions. We write each step of working one at a time, working down the page, and we write our equal signs in a straight line. For the equation 6y equals 18, the variable y has been multiplied by 6 to get the expression 6y. The equation tells us this equals 18. Working backwards, we do the inverse of multiplying by 6, dividing by 6, and get to the value 3. So the solution is y equals 3. The next equation has had two operations applied to the variable t. We need to use the order of operations to make sure we're applying those operations in the correct order. So the first thing done to t is subtracting 8, and then that whole quantity is multiplied by negative 5. To work these steps backwards, we need to divide by negative 5 and add 8. So 30 divided by negative 5 is negative 6, and negative 6 plus 8 is 2. So we can write out our full working and find the solution t equals 2. For the next equation, we have the variable n, which has been divided by 4, and then that value has had 11 added to it, to get the value 5. Working backwards, we will subtract 11, and then multiply by 4. 5 take 11 is negative 6, and negative 6 times 4 is negative 24. If we write this out in the more conventional form, we get our solution, n equals negative 24. We need to be a little more careful in our next equation, because there have actually been 3 different operations applied to the variable. So starting with our variable x, we know that we need to evaluate this numerator in this fraction before we do anything else. So the first thing that's done is multiplying by 3, and then 9 is subtracted from it. Finally, that entire value is divided by 2. The equation tells us that the result is 6. Now, working our operations backwards, we need to multiply by 2, add 9, and divide by 3. 6 times 2 is 12, 12 plus 9 is 21, and 21 divided by 3 is 7. As before, let's write out our working in a more conventional form, ending with the solution x equals 7. The properties of equality. We've recently learned about some important algebraic properties, the associative, commutative, and distributive properties. Well, for us to keep working with equations, there are some other properties that we need to know. The properties of equality. Let's start with the addition property of equality. Suppose we have two values which we know are equal. Let's call them A and B. Well, what if we were to add the same value, let's call it C, to both of those values? So we have A plus C and B plus C. Well, the addition property of equality says that these two also have to be equal. And in fact, it works the other way as well. The only way that the first two values, A and B, are equal are if we still get something equal when we add C. What this really means is that equality isn't changed by adding. Now we can continue with the same idea for subtraction, multiplication, and division. There's one small caveat. For multiplication and division, we need to be careful when working with 0, because multiplying by 0 just turns everything to 0. So things end up being the same, even if they weren't the same to begin with. And we can't divide by 0 because, well, dividing by 0 causes all sorts of other problems. Solving method 2. Balancing each side. We can imagine an equation as a scale whose two sides perfectly balance. The scale remains balanced as long as we always do the same to both sides. Let's illustrate the equation x plus 5 equals 12. We can represent the variable x with a bar of unknown weight, and each of 5 and 12 can be represented using unit blocks. Now we know that this scale will be in balance because the equation tells us that these two values are equal. Now remember, our scale will stay in balance as long as we do the same thing to both sides of the equation. In this case, we can remove 5 unit blocks from both sides of the scale. What we find is that on the left-hand side, we just have our variable bar x, and on the right-hand side, we have 7. Now, mathematically speaking, what we've done is subtract 5 from both sides of the equation. Doing so gives us the solution, x equals 7. Let's illustrate 4x equals 20. Now, 4x means 4 times x. So to represent that, we need 4 of our bars for our variable. To represent 20, we'll use unit blocks again. Now, if we share our unit blocks evenly, we can make 4 groups of 5. These 4 groups have the same weight as the 4 variable bars. That means one variable bar is the same as one of these groups. So our solution is x equals 5. Now what we've done in practice here is divide both sides of the equation by 4. 4x divided by 4 is just x, and 20 divided by 4 is 5. Our solution is x equals 5. Let's illustrate 5x plus 9 equals 24. So on the left-hand side, we have 5 variable bars and 9 unit blocks. And on the right-hand side, we have 24 unit blocks. Now we can simplify this by taking away the 9 unit blocks on the left-hand side. But remember, to keep our scale in balance, we need to do the same thing to the right-hand side. This leaves us with 15 unit blocks on the right. These can be shared equally into 5 groups of 3, which correspond to the same weight as 5 variable bars. This means that one variable bar has the weight of 3, which is our solution. Now again, in practice, what we're doing is applying the same operations to both sides of an equation. So 5x plus 9 equals 24 can be simplified by subtracting 9 from both sides, which gives us 5x equals 15. Then we can divide both sides of the equation by 5 to get the solution, x equals 3. Let's practice some examples without using a model to support us. So we're going to use the same ideas we've already seen, but we're just going to work with them algebraically. N take 17 equals negative 3. The inverse of taking 17 is adding 17. If we do this to both sides of the equation, we get n equals 14. B divided by 7 equals 9. The inverse of dividing by 7 is multiplying by 7. So if we do this to both sides of the equation, we get the solution b equals 63. Negative 3t equals negative 39. The inverse of multiplying by negative 3 is dividing by negative 3. If we do this to both sides of the equation, we get t equals 13. Negative 39 divided by negative 3 is 13. 2u take 9 equals 15. The last operation applied to the left-hand side was subtracting 9. So to remove it, we apply the inverse, which is adding 9, which leaves us with 2u equals 24. To find u, we can divide both sides by 2. Remember that 2 in front of the u is multiplying it, and we need to do the inverse. 24 divided by 2 is 12, and that's our solution. U equals 12. The quantity x plus 15 divided by 4 equals 3. The last thing applied to the left-hand side here was dividing by 4. So the inverse is multiplying by 4. If we apply that to the right-hand side as well, we get 12. X plus 15 equals 12, which we can simplify by subtracting 15 from both sides. This leaves us with x equals negative 3, our solution. 2 times the quantity y plus 5, and then subtract 7, is equal to 27. The last operation being applied on the left-hand side is subtracting 7. So we can do the inverse, which is adding 7. Doing this to the right-hand side gives us 34. Now the next to last operation applied to the left-hand side was multiplying by 2. So we do the inverse, which is dividing by 2. 34 divided by 2 is 17. So y plus 5 equals 17. Finally, the inverse of adding 5 is subtracting 5. Applying this to both sides, we get that y is equal to 17 subtract 5, which is 12, which is our solution. Let's finally look at an application of solving an equation. Jessica is a member of a gym that charges $45 for membership and an extra $6 for each visit. Jessica has paid $87 in total to the gym. How many visits has Jessica made to the gym? Now, before we can use an equation to solve a problem, we need to know what variable it is that we're trying to solve for. The question we're trying to answer is how many visits Jessica has made to this gym. So we're going to use the variable v. I'm using it to stand for visits. And we're going to write let v be the number of visits Jessica made to the gym. Now that we have this, we can write down an equation. We can work out how much Jessica has spent in total using our variable. That's $45 for membership, plus 6 times the number of visits that she's made. Now, unlike when we were dealing with problems like this with expressions, we actually know what this equals. We know that she has spent $87 in total. So we can make our expression equal to 87. This is the equation that we're trying to solve. The last thing that's been done to our variable v has been adding the value 45. So this is the first thing we need to undo. The inverse of adding 45 is subtracting 45. So we find that 6v, which represents the cost of the 6 visits without the membership fee, is $42. To find the cost of a single visit, we need to divide by 6, which gives us the solution, v equals 7. Now, when answering an application question like this, we should always answer the question in the context that the question was asked, because v equals 7 is somewhat meaningless by itself. So our actual answer is that Jessica made 7 visits to the gym, because that is the actual meaning of the solution that we found.